Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be finishing up our chapter on fluids. So far, we've covered the fundamentals of fluids at rest, and now it's time to explore how fluids behave when they're set in motion. This branch of fluid mechanics is known as fluid dynamics, and fluid dynamics is essential for understanding everything from the flow of blood in our veins to the way airplanes glide through the sky. One of the first concepts we need to address in fluid dynamics is viscosity. Viscosity refers to the internal resistance of a fluid to flow. It's essentially a measure of how thick a fluid is. Fluids like water and ethanol, they have low viscosity, meaning they flow freely and easily. And the reason for this is because these fluids experience minimal internal friction. On the other hand, fluids like molasses and tar, they have high viscosity. They resist motion because their internal friction is much higher, and that causes them to flow slowly. Now, the SI unit for viscosity is the Pascal second, and this is equivalent to 1 Newton second per square meter. Understanding viscosity is important because it influences how fluids move through pipes, how they mix, and how they respond to forces. On that note, when a fluid is moving, its flow can be categorized as either laminar or turbulent. Laminar flow occurs when a fluid moves in smooth, orderly layers, with each layer sliding past the adjacent ones without mixing. Turbulent flow, on the other hand, is characterized by chaotic and irregular movement. With these definitions in mind, let's elaborate on both in more detail, and we're going to start with laminar flow. Laminar flow represents the most orderly way a fluid can move. Imagine a gentle stream of water flowing through a narrow pipe, where every droplet follows a straight path, gliding past each other in layers without mixing or creating any disturbances. This is the essence of laminar flow. It's smooth and predictable. Now, the key to understanding laminar flow really lies in visualizing the fluid as moving in parallel layers. These layers, often referred to as streamlines, flow together without intersecting. So to picture this, imagine a stack of papers sliding over one another. Each sheet moves independently, yet remains aligned with the others. This is how laminar flow maintains its steady motion. Now, to that, I want to make a note, and that note is that the velocity of the fluid varies across these layers. It's fastest at the center of the pipe, where frictional resistance from the walls is minimal, and it's the slowest near the edges, where friction is greatest. Now, the next thing we want to do is we want to dive into what governs this flow and how we can quantify it. When a fluid moves through a confined space like a pipe, several factors come into play. The flow rate, or the volume of fluid moving per unit time, it's influenced by a couple of things. It's influenced by the radius of the pipe. It's influenced by the pressure difference across the length of the pipe. It's also influenced by the viscosity of the fluid, as well as the length of the pipe itself. All of these variables come together in a relationship known as Poiseuille's law. Now, I've seen different pronunciations of this law. I'm just going to say Poiseuille's law. If you have a problem with that, please take it up with the French and leave me be, okay? Now, Poiseuille's law, it gives us a precise way to calculate the flow rate of a viscous fluid through a cylindrical pipe. The law states that the flow rate is directly proportional to the fourth power of the radius of the pipe. This means that even a small increase in the radius results in a significant increase in the flow rate. So for instance, doubling the radius of the pipe doesn't just double the flow rate, it actually increases it by a factor of 16. This sensitivity to the radius is why blood vessels, for example, need to maintain a precise diameter to ensure proper blood flow throughout the body. Now, the law also tells us that the flow rate is directly proportional to the pressure gradient along the pipe. So a greater pressure difference between the two ends of the pipe drives the fluid more forcefully, resulting in a higher flow rate. On the other hand, the flow rate is inversely proportional to both the fluid's viscosity and the length of the pipe. So a thicker, more viscous fluid resists motion more than a thinner one, and that reduces the flow rate. Similarly, a longer pipe introduces more resistance due to friction, further hindering the flow. Now you might be asking, why does this matter? Well, in the medical field, for example, understanding laminar flow is really important for comprehending how blood circulates in our bodies. Again, blood vessels can be thought of as pipes, with blood as the fluid moving through them. If a blood vessel narrows due to plaque buildup, for example, even slightly, the resistance increases dramatically, which can reduce blood flow to vital organs. And that obviously highlights the importance of maintaining open and unobstructed pathways. Now, what about turbulent flow? While laminar flow is characterized by its smooth, orderly layers of fluid, turbulent flow represents the opposite end of the spectrum, where fluid particles move erratically, mixing and swirling in all directions. Turbulence is what happens when the orderly layers of laminar flow break down and create a disordered state where the fluid moves in complex, irregular patterns. But how does a fluid transition from laminar to turbulent flow? The key lies in the fluid's speed and certain physical characteristics which determine whether the fluid will maintain its orderly motion or devolve into chaos. This transition is governed by a concept called critical speed. When a fluid flows through a pipe or over a surface, as long as its speed remains below a specific threshold, the critical speed, it will continue to flow in a laminar manner. However, once this critical speed is exceeded, the smooth layers break down and you're going to get turbulent flow instead. The critical speed, this can be determined using the following relationship. So in this equation, critical speed is equal to Reynolds number, this is a dimensionless constant, multiplied by the viscosity of the fluid, and then this is divided by the density of the fluid and the diameter of the pipe or channel through which the fluid is flowing. Now, Reynolds number, this plays a crucial role in fluid dynamics. It quantifies the relative importance of inertial forces to viscous forces in the fluid. A low Reynolds number indicates that viscous forces dominate, leading to laminar flow. A high Reynolds number, on the other hand, means that inertial forces are more significant, which can lead to turbulence. When the critical speed is surpassed, turbulent flow takes over. In this state, the fluid exhibits complex flow patterns where energy is dissipated through the formation of swirls and vortices and eddies. These swirling motions, often seen behind obstacles or in fast-moving streams, they create regions of high and low pressure, making the flow highly unpredictable. Now, what is interesting is that even in turbulent flow, there is a small region near the surface of the pipe or obstacle where the fluid actually remains relatively orderly. This thin layer of fluid adjacent to the wall, this is known as the boundary layer. Within this layer, the fluid moves in a laminar fashion. But as we move away from that boundary layer, the flow becomes increasingly chaotic. The thickness of the boundary layer, this is influenced by the Reynolds number and the roughness of the surface. Just as laminar flow, though, turbulent flow also has practical implications and applications. So, for instance, turbulence is crucial in mixing processes, such as in chemical reactors, where it is important that reactants are well mixed and reactions can occur efficiently in that manner. In aerodynamics, understanding turbulent flow around wings and aircraft bodies is really essential for reducing drag and also improving fuel efficiency. Now, we've explored flow. It's natural to now wonder how we can make sense of fluid movement when individual molecules move in such complex patterns. Tracking each molecule is impossible, so to simplify the analysis, we use visual tools like streamlines. Streamlines are a way to represent the paths followed by tiny fluid elements as they move, and it helps provide a clearer picture of the overall flow of the fluid. So imagine streamlines as invisible trails that show the direction of fluid motion at every point, much like the paths left by leaves floating on a stream. Streamlines help us understand fluid motion by indicating how different parts of the fluid are moving. So in laminar flow, the streamlines are smooth and parallel, and they show a predictable path for each particle. In turbulent flow, on the other hand, these lines would be twisted and chaotic, reflecting the disorderly nature of the fluid. And we kind of saw that in each section. So here we see streamlines for turbulent flow, and up here we see streamlines for laminar flow. One of the key characteristics of streamlines is that the velocity of the fluid is always tangent to the streamline at any point. This means that fluid particles follow these paths exactly, never crossing over from one streamline to another. This property makes streamlines invaluable for visualizing and analyzing fluid behavior in a variety of situations. To further understand fluid flow, we want to turn our attention to the continuity equation. This is derived from the principle of conservation of mass, and it helps us quantify how fluid moves through different sections of a pipe or channel, ensuring that the mass flow rate remains constant. This equation is expressed in the following way, where we see that Q is equal to V1A1, and that is equal to V2A2. Here, Q represents the flow rate, or the volume of fluid passing through a section per unit time. V1 and V2 are the linear speeds of the fluids at point 1 and 2 respectively. A1 and A2, these are the cross-sectional areas of the pipe at these points. This equation tells us that the product of the fluid's speed and the cross-sectional area must be the same at any 2 points along a streamline in a closed system. This means that if the area of the pipe narrows, the speed of the fluid must increase to maintain a constant flow rate. This is why water flows faster through a narrow nozzle than through a wide pipe. Now let's take this concept one step further and understand the energy dynamics of fluid flow using Bernoulli's principle. Bernoulli's principle states that for any incompressible, non-viscous fluid flowing along a streamline, the total mechanical energy of the fluid remains constant. This principle is a powerful tool for understanding how pressure, velocity, and height interact in a moving fluid. The mathematical expression of Bernoulli's principle is given by Bernoulli's equation, which you see here. In this equation, we have P1 plus 1/2 rho V1 squared plus rho multiplied by G multiplied by H1. And this is equal to P2 plus 1/2 rho V2 squared plus rho multiplied by G multiplied by H2. Now in this equation, P1 and P2 represent the static pressure at points 1 and 2. These terms right here, 1/2 rho V squared, these represent the dynamic pressure, which is related to the fluid's velocity. And then these last terms, rho GH, these represent the gravitational potential energy per unit volume at these points. According to Bernoulli's principle, the sum of these three forms of energy, pressure energy, kinetic energy, and potential energy, they remain constant along a streamline. This means that if a fluid speeds up, its kinetic energy increases, and to compensate, its pressure or height must decrease. Now, one of the most intriguing applications of Bernoulli's principle is seen in the venturi effect. This is elegantly demonstrated by the venturi flow meter. This effect occurs when fluid flows through a pipe that narrows and then expands again. As the fluid enters the narrow section, its velocity increases to maintain the continuity of flow, as described by the continuity equation. But as the fluid speeds up, something else happens. Its pressure drops. And this is a direct consequence of Bernoulli's principle, which tells us that as the kinetic energy of the fluid increases, the pressure energy must decrease to keep the total energy constant. Now, let's try to imagine this in action. And let's imagine this using a flow meter. All right, this is going to consist of a tube with a constricted throat in the middle. As the fluid enters the wide section of the tube here at point 1, it's going to move at a certain speed V1. And it's going to exert a pressure P1 on the walls. Then as the fluid reaches this narrower part at point 2, the cross-sectional area here is going to decrease. And according to the continuity equation, the fluid must speed up to maintain the same flow rate. This increase in speed, however, is going to lead to a drop in pressure P2. We can see the results of this pressure drop in this diagram here, where the height of the fluid column above point 2, all right, the fluid column above point 2, it's lower than that above point 1 right here. This lower height indicates a decrease in pressure, and it illustrates this venturi effect. The fluid's desire to balance the energy budget is going to result in a lower pressure at that narrow section. And it's really important to know that this phenomenon has wide-ranging implications. And we're going to see a little bit of that in our last and final objective, where we discuss fluids and physiology. To wrap up our exploration of fluid dynamics, we now want to turn our attention to the role of fluids in the human body, particularly within the circulatory and respiratory systems. These systems, though complex, are governed by the same principles of fluid dynamics and pressure that we've been discussing up until this point. The circulatory system, it behaves as a closed system, meaning that blood circulates in a loop throughout the body, and it's propelled primarily by the heart. The heart acts as a pump, generating pressure differences that drive blood flow through the arteries and veins. When the heart contracts, it creates a high pressure wave that pushes blood through the arteries. Then, as the heart relaxes, the pressure drops, and that allows the heart chambers to fill with blood once more. Now, we also want to discuss the respiratory system. In this system, the primary function is to facilitate gas exchange, allowing oxygen to enter the bloodstream and carbon dioxide to be expelled from the body. Now, when you inhale and exhale, these processes are driven by changes in pressure within the thoracic cavity. During inhalation, the diaphragm and the intercostal muscles, they contract, expanding the thoracic cavity and reducing the pressure inside the lungs relative to atmospheric pressure. This pressure gradient, it causes air to flow into the lungs. On the other hand, when you exhale, these muscles relax and the thoracic cavity decreases in size and the pressure inside the lungs increase, and that allows air to be pushed out. These pressure changes are really important, not just for breathing, but also for the circulation of blood. For instance, the process of inhaling creates a negative pressure in the thoracic cavity, which helps draw blood into the large veins returning to the heart. This demonstrates how the respiratory and circulatory systems are also interlinked. So, in summary, the principles of fluid dynamics and pressure regulation are really fundamental to the functioning of both the circulatory and respiratory systems. And understanding these principles provides us with valuable insight into how blood flows through our bodies, how air moves in and out of our lungs, and how these systems work together to maintain homeostasis. With that, we've covered all the objectives that we need to in this chapter. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.